So, here we are again, chemistry video number 32. Thank you, COVID-19. This is going to be a review of electron configuration because, you guys have to understand the way it's set up. So first of all, like we said before, J.J. Thomson, super smart, about 1897, somewhere around there, he shot this beam toward a positive and negative plate, and the beam really bent up toward the positive plate. So he said, whatever this beam is made of, got to be really light because it's bent up so much, and he called them electrons. And then Niels Bohr, in about 1913 or somewhere around there, he goes, you got to look at an atom like our solar system. And electrons are found in orbits going around like this. And that's a great way to look at it. And then later on, the modern theory or the modern model of the atom is, no, electrons aren't in orbits. They are in things called orbitals, and they don't have a single plane like the planets do. They go all around. So now we know that electrons are in orbits, but there's a lot more going on than that. So here's an analogy. You are at the ground level and you have to get up 7 steps to get to your house. Well, the ground level is like where the nucleus is, and you're an electron. And so there's the analogy. So you're at the ground level, and in order to get up to that first step, you have to have energy put into you to get to the first step. All right? Same thing with an electron. Electron is at the first step, which is like called an energy level. It doesn't really want to go up there. It wants to be at the ground level like you are. You're more stable and safe at the ground level. When you start going up steps, you become unsafe. Same thing with electrons. When electrons start going up steps, which are called energy levels, they don't like it up there. They want to be back down where they were. They want to be at the ground level. So, you're standing there on the ground, and you don't want to go up those steps, but somebody pokes you in the back, and you jump up to the first step. Well, if you don't have enough energy, you're not going to make it to the first step, so you're going to still be at ground floor, right? Same thing with an electron. If you give an electron energy and it doesn't have enough energy to jump to the second energy level, it's going to stay at the first. All right, so let's just say you're enjoying yourself at the ground floor, you don't want to go up those steps, and somebody really pokes you in the back, and you jump up to the third step. Well, that can happen to an electron. An electron is close to the nucleus, it's chilling out, enjoying itself, super stable, then it gets a whole bunch of energy, and it can jump all the way to the third or fourth energy level. It doesn't like it up there. You don't like it up there on the third step. So, do you need energy to jump back down? No. Does an electron need energy to jump back down to be safe near the ground? No. You just walk to the edge of the step and then jump. So, you're actually giving off energy by jumping down the steps, trying to be more stable at the ground level. Same thing with an electron. If an electron's way out, like on the 5th, 6th, 7th step, which means energy level, doesn't like it out there. Too unstable, wants to go back where it started. So it gives off energy. So these steps that I'm talking about have a whole bunch of different names for the electrons. So let's write a couple of them down. The first name is, instead of 1, 2, 3, 4, 5, 6, 7 steps for electrons, it would be 1, 2, 3, 4, 5, 6, 7 energy levels. So, Roman numeral 1. Energy levels, okay? Another name would be, instead of energy level 1, 2, 3, 4, 5, 6, 7, you could say quantum number 1, 2, 3, 4, 5, 6, 7. In high school chemistry, I don't really use quantum number. I like energy level, but the one we use the most is this. Instead of saying steps 1, 2, 3, 4, 5, 6, 7 for electrons, or energy level 1, 2, 3, 4, 5, 6, 7, I just call them shells. Shell 1, 2, 3, 4, 5, 6, 7. So here is where the electrons are. We know they're in orbitals, but the orbitals can be in energy levels or shells 1, 2, 3, 4, 5, 6, 7. And we already talked about if you're close to the nucleus or close to the ground floor, you're super stable. That's where the electrons want to be. They want to be close to the ground or the nucleus. If you're out in 5, 6, or 7, shell 5, 6, or 7, or you are on step 5, 6, or 7 going up the steps, you're unstable. You don't like it up there. You want to go back where you were before. Okay? So these are called energy levels. Now, they actually coincide with your periodic table, because on the left-hand side of the periodic table, it has the word period, and it goes period 1, 2, 3, 4, 5, 6, 7. Well, that's the same thing as an energy level or a shell. So I had you write energy level or shell next to period. And so now we know that going across horizontally, you have energy level 1, 2, 3, 4, 5, 6, 7. Okay? Now, these energy levels, how many electrons can fit in each energy level? That's the next thing we have to figure out. So, Roman numeral 2. So it just says, Roman numeral 2, number of electrons in each shell. Well, there's a handy-dandy formula. And the formula is this. 2n squared. And n stands for the shell number. It's pretty easy if you can do your math. 2n squared, n is the shell number. So what we're going to do is we'll go down 1 through 7. And now if you plug in one shell. Remember, the first shell, that's where you want to be. It's the most stable. It's like you being on the ground level. It's electrons close to the nucleus, they're safe there. So, 2n squared. 1 squared is 1 times 2, so we have 2, a maximum of 2 electrons in the first shell. Now the second shell, 2 squared is 4 times 2 is 8, so we have 8 electrons. And so on. So the next one we have 18 electrons, because that would be 3 times 3 is 9 times 2. Then we have 32 electrons. And these, the first 4 shells, they're the most important for high school chemistry. But let's go on. 5 times 5 is 25 times 2, that's 50 electrons. 6 times 6 is 36 times 2, that's 72 electrons. And then 7 times 7 is 49 times 2, that's 98 electrons. That's how many electrons that could fit in each energy level or shell. But like I said, we are mainly concerned with shells 1, 2, 3, and 4, or energy levels 1, 2, 3, and 4. All right? So that's how many electrons can fit in each energy level or shell. Now, there's something smaller than a shell, and it's called a subshell. So, Roman numeral 3. So, Roman numeral 3 is subshell, or sometimes they call it a sublevel. Because you have energy levels, then you have the level below an energy level, and that's called a sublevel or subshell. Now, there are 4 subshells. There are 4 subshells. So, the first subshell is called the S subshell. Now, this subshell is found in every single shell or energy level. I don't care if you're 1, 2, 3, 4, 5, 6, or 7 energy levels. The shell always must start out with an S subshell, always. So if you think of it, you know, it would be like the frame of a car. You put the engine on the frame, you put the tires on the frame, you put the body on the frame. If you don't have a frame, you can't build a car. Well, the same thing here. The S is the frame of all the shells. So we start out with S, all right? And a couple things about S. Every single shell has to start out with an S subshell. Every single one. Now, I'm not going to tell you how many electrons are in there yet. We're going to do that a little bit later on. Now, the other thing about S is if every shell starts out with an S, then that means that's where electrons go first. That means it's the most stable subshell. So here, what I want you to write down for number 2, most stable subshell. It is the most stable subshell. Now, for number 3, the interesting thing about this subshell is it can only have a max of 2 electrons. So for number 3, if you'll write down max 2 electrons. That's all it can have. Max of 2 electrons. All right? Okay. So that A is the S subshell. Now we're going to put down letter B. And letter B, like I said, A, the first subshell is the S. Letter B, the second subshell is the P subshell. The P subshell. Okay? That's the next most stable. And for number 1, I'll just tell you what the max is and we'll move on. The max number of electrons in the P is 6. So the maximum number of electrons in the P is 6. Okay? All right, that's the P subshell. So we've gone over S subshell, P subshell. Now, for letter C, this is called the D subshell. And the D subshell can hold a max of 10 electrons. Now, the further we're going, the more unstable they are. So S is the most stable subshell to be in if you're an electron. Then P, then D, and then the most unstable subshell is our next one. This is letter D. And the most unstable subshell is called the F. That's way out there. And this has a max of 14. Max of 14 electrons. So now we're going to put everything together. The first column is shells or energy levels. Remember, we have 1 through 7, but the most important ones are just 1 through 4. Shells are made up of subshells, S, P, D, and F. And then finally, subshells are made up of things called orbitals. We haven't talked about them yet. We will. All right, so the first shell. Now, the first shell, by using 2n squared, can have a max of 2 electrons. That's all. It's the most stable shell to be in. And remember, every single shell got to start with a frame. And the frame is the S. So the only subshell in the first shell is the S. Now we'll talk about orbitals later on. In the second shell, 2 squared is 4 times 2, that's 8 max electrons. Now watch how this works. Every single shell starts with an S. Every one. Now, this S would take 2 electrons away from the total of 8, which leaves you 6 electrons left in that shell, and that would mean those 6 electrons would be loaded in the P subshell. So we have S and P. Now, third shell. Third shell has a max of 18 electrons. Cool part. S takes up 2 of those. P takes up 6. That's 8 of those electrons gone. So I have 10 left, and that's exactly how many a D subshell can fit. SPD. 4. So 4 times 4 is 16, times 2 is 32 electrons. Now, S takes up 2, P takes up 6, D takes up 10, and that's 10, 6, and S, that's 18 electrons out of 32. I'm left with 14 electrons left, and that's exactly how many can fit in an F. So watch how easy this is. In the first energy level, we have 1 subshell, S. Second energy level, 2 subshells, SP. Third, we have 3, SPD. Fourth, we have 4, SPDF. Now, what the heck is this orbital stuff? Here's the deal about orbitals. We're going to write it down later on, but we might as well figure it out right here. An orbital can hold a maximum of 2 electrons. Now, I always have my classes try this, and very few people can do it on the first try. In that orbital that has 2 electrons, the electrons have opposite spin. So put your fingers like this, bring one toward you and one away, and then back up. This is opposite spin, and that's for stability. So each orbital can hold a max of 2 electrons, and they have opposite spin. So look, S only has 2 electrons. So S would only have 1 orbital. Now, P has 6 electrons, so that would have 3 orbitals. So 1 orbital from S, 3 orbitals from P. So the second shell could have a maximum of 4 orbitals. Now, we have 18 electrons here. 1 orbital in the S, 3 in the P, and that would mean 5 in the D. So 5, 6, 7, 8, 9. We have 9 orbitals in the third shell. And finally, we have 32 electrons, and we have 1 orbital in the S, 3 in the P, 5 in the D, 7 in the F. Okay? So, all you have to do is 7 and 5, 12, 13, 14, 15, 16 orbitals in the fourth shell. So that's how many orbitals. Now we're going to go further into orbitals, but that's what it looks like. So my question, what shell, what subshell would you like to be in to be the most stable? Well, the most stable is in the first shell, and it's the S subshell. That's the most stable. Which of these on the board would be the least stable? The least stable would be being in the fourth shell and the F sublevel. You don't want to do that. You're way out there. You got a ton of energy. You don't want to be out there. Okay? So that's what this is. Now, the next thing is we have to talk a little bit more about orbitals. So, some background for orbitals. We already talked about that. Orbital. Max 2 electrons. Opposite spin. Remember, that's for stability. So now we have to talk about the S orbital. S orbital. Like I said before, that's closest to the nucleus. That's the first orbital that gets filled in the shell, so it's the most stable. Most stable. And we might as well put down can only hold 2 electrons. It has a spherical shape. Think about a beach ball, think about the skin of the beach ball, and that's where the electrons would be, spherical. So they're moving in a sphere, spherical shape, all right? And once again, every shell starts with an S, but now for letter D, we have to draw a picture of that. So let's go like this. Here's my X axis. Here's my y-axis. Here is my z-axis. Now don't forget, X is horizontal, Y is vertical. Now this Z is, the straight part is here, and the dotted line is behind the blackboard. Okay? So, and then what would an S orbital look like? It would look like this. Just like that. So an S orbital is spherical, and it looks like that. The most stable can only hold 2. Every shell starts with 1. All right, that's the S. Now let's just talk about the P orbitals. Max 3 electrons. I'm sorry. Max 6 electrons. Number 2, if it's got 6 electrons and each orbital can hold 2, so this would be contains three orbitals. All right? And the third one, dumbbell or figure eight shape. Instead of spherical, they look like figure eights or dumbbells. So I'm going to draw this one, and then we don't have to worry about what D looks like. We don't have to worry about what F looks like. So we're just concerned with S and P orbitals. All right, so for number, this isn't a number. This is going to be just what it looks like. Here we go. So same axes. There's my X. There's my Y. And there's my Z. Now, if the orbitals are figure eight, let's start with X. X would look like this. And there's my figure eight or dumbbell shaped. So that's what the electrons would do in the P sub X orbital. So we could call this P sub X. That's the P sub X. So what would the P sub Y look like? Same thing. So there is the figure eight for P sub Y. And finally, P sub Z. P sub Z would look like this. So that's P sub X, P sub Y, and P sub Z. Okay? So that's what it would look like. And remember, if we had an S orbital to start out the whole thing, the S orbital would kind of look like this. So there would be the S orbital, and this would be the P sub X, P sub Y, P sub Z. Okay? That's the shape. So we're only concerned with the S and P orbitals. All right. So the most important thing about orbitals, since we're doing electron configuration, is how are orbitals filled? And here's a rule, and you'll see what it means in just a little while. So at one electron in each orbital before two electrons in any other orbital. So what that means, really boiled down, is one in each before two in any. And you'll see what that means in just a minute. Okay, now we get on to the good stuff. How would all this be used? Well, let's take oxygen. So oxygen is this, O816. Now remember, if that is an atom, that means that the atomic number not only tells you the number of protons, it also tells you the number of electrons. So that is an atom, it's neutral, it's got 8 electrons, okay? So we got to figure out if it's got 8 electrons. Well, where would they load? Well, remember what I said, the first energy level or shell is the most stable, so that's where they'd start. So the electron configuration for oxygen would look like this. First shell, that's where they would start to load. Every shell starts with an S. So this means the first shell. This is the S subshell. And I got 8 electrons to play around with. I only need 2 to fill in the S. So I have first shell, S subshell, and I can put a 2 right there. So now watch what that means. This is the shell. This is the subshell. And this is the number of electrons in the subshell. So that's what it looks like. 1s2, first shell, S subshell got 2 electrons. And we know, because you memorized, the first shell can hold 2 electrons, the second shell can hold 8 electrons, third shell can hold 18 electrons, and the fourth shell can hold 32 electrons. So I've got 8 electrons to use, and I've already used up 2 of them, so the first shell is gone. So where do I go now? Well, if the first shell is gone, I have to go to the second shell. So I'm going to put a 2. Now, every shell starts out with an S. So I had 8 electrons. The first shell sucked up 2. That means I still have 6 electrons left. So the first subshell in every shell is an S. So I put 2s. Now how many electrons max can fit in the S? 2. So I put 2s2. Now, look, I've used up 2 electrons in the first shell, and I've used up 2 electrons in the second shell. Well, the second shell can hold a max of 8. Well, I've used up 4 of the 8. I still got 4 electrons left. Where am I going to put them? Am I going to go to the next shell? No, because my second shell needs to be filled first. So I have to go like this. I'm still in the second shell, 2, and a P subshell is in the second shell, so I got to put P. And so how many can fit in the P? Max 6. Do I have 6? No. I only have 4 electrons left. So it will be 2p4. So that is the electron configuration for oxygen. Now, I like that configuration, but I also like something called dash. So if I said do the dash of this, you'd see how many would be in each shell. Well, here's the first shell. I got 2 there. So that'd be 2 dash. Here's the second shell. Don't forget, the second shell is both the S and the P. Add them together. 2 and 4, 6. So the dash for this would be 2-6. So this is the configuration. This is the dash form. And all the electrons filled in closest to the nucleus, which means they're really stable. All right? It's just like us standing on the ground. We're stable there instead of going up the steps. So this, when all the electrons fill nice and neat close to the nucleus, is called ground state. This is called the ground state, where all the electrons fill in nice where they're supposed to be. Now don't forget, if I put some energy in there, some of these electrons could jump out. But we're not going to talk about that right now. We got to do a lot of these so you understand. And the cool part about it is this right here, 2-6, if you look on your New York State reference tables, this 2-6 is directly underneath the symbol for oxygen. And that's how they get the 2-6. All right, let's do a few more. But the problem now is this. That's how they get that. Now we have to look at the orbitals. All right, remember we said 1 in each before 2 in any. What the heck does that mean? So, watch. All right, S has 2 electrons. It can have 1 orbital. Remember, S has 1 orbital, P has 3, D has 5, F has 7. So S has 1 orbital. So I'm going to draw it like this. I'm going to draw a square, and 1 arrow up and 1 arrow down. So the square is the orbital for S, and 1 arrow up, 1 arrow down means opposite spin. So for our case, squares are always going to be the S's, and circles will always be the P's. So there's 1. Now I have S2. Well, that's another square. One up, one down. All right, that's perfect. Now, for p orbitals, I'm going to make them circles. And p can hold 3 orbitals. So I'm going to go like this. 1, 2, 3. Now, the rule, 1 in each before 2 in any. I have 4 p electrons. 1 has to go in each orbital before I put 2 in any. So I got 4. So here goes 1, 2, 3, and 4. That's what the rule means. 1 in each before 2 in any. So I have 1 filled orbital, 2 filled orbitals, 3 filled orbitals, and 2 half-filled orbitals. You understand that? Now the orbitals give rise to something called electron dot. But we're not going to do that now. We got a lot of these to do. But I have to tell you this though. The outside shell is where all the action is. All right? And here's the outside shell. Right there. The second shell is the outside shell. So whatever shell is the outside shell, it's called the valence shell. The valence shell is the outside shell, and that's where all the action is. We'll talk about that a little bit later on. Okay? All right, let's do a couple more of these. I am going to give you let's do aluminum. So I got Al 13. So remember all our rules, so let's look. We got 13 electrons to mess with. The most stable, absolutely most stable shell or energy level is the first one. So we go 1s. I got 13 electrons, so I know the first shell's filled, 1s2. So my second shell, 2s, because every shell starts with an s, 2. So far I've used up 4 out of the 13 electrons. Now, I'm still in the second shell, 2p. P can hold 6 electrons. Do I have enough electrons to load up that? Well, I've only used 4 out of the 13, so I do. So I go 2p6. So now look at 2, 2, 6. I've used up 10 of those 13 electrons. My first shell has 2 in it. My second shell has 8. Both those shells are filled. Where do I go now? My third shell. Now, in my third shell, every shell starts with an S. So I'm going to put an S. And remember, I only had 3 electrons left to mess around with. So 2 can fit in there, 3s2. And I only have 1 electron left to plug in. Well, the 3s is filled, so I have to go to the next subshell, and that's a p. So it will be 3p1. And that's what aluminum looks like. And now let's circle the valence shell. The outside shell is the valence shell. And now let's do dash. So I'm going to put the dash above it. How many electrons in the first shell? 2. Dash. How many electrons in the second shell? 2 and 6, 8. How many electrons in my valence or last shell? 3. 2, 8, 3. And that's how aluminum is filled up. And that's, remember, they're all stable, so that's called the ground state again. Now let's see about orbitals. And this is a different way to do orbitals. I'm going to make them all circles. So S2, that's filled. S2, that's filled. P6, 1 in each before 2 in any. All right, that's filled. S2, filled. 3 orbitals, and I only have 1 in the P. So how many filled orbitals? 1, 2, 3, 4, 5, 6 filled orbitals and 1 half filled orbital. Okay? All right, now we're going to get a little bit tougher. Now this is going to have a different rule. So we're going to go like this. We're going to do Ca20. Now we have 20 electrons to mess around with. 20 of them. Okay? All right, so here we go. If we have 20, we know the first 2 shells are filled. I mean, we have 1s2. That takes up 2 electrons. 2s2. 2p6. So I've used up 10. I still have 10 electrons left. So I go 3s2. So I've used up 12. 3p6. So look it. I've used up 12, 13, 14, 15, 16. I've used up 18. I've got 2 more electrons left. All right? Now, this is a big sticking point for everybody. I got 2 electrons left, and everybody goes, oh, let's just go 3d2. You can't do that. Listen to my rule. This is huge, and it's going to be tested on. The maximum number of electrons in any outside shell, which means any valence shell, is 8. You can't have any more than 8 in the outside shell. If you do, you got to jump to the next shell. All right? I know it doesn't make sense right now, but it will. So I have, when we do dash, I have 2, dash 8, and then this right here is 8. I can't have more than 8 in the outside shell, so I can't put a 3d2 there, because that would be more than 8 in the outside shell. So what do? I got to jump to the next shell. So the next shell is the 4th shell. So it goes 4, and I have 2 more electrons to put in there, s2. So I got past my rule. Because I have 8 in the outside shell, I jump to the next shell. So this would be 2, 8, 8, 2. And that's exactly what's underneath calcium. Okay? Now, this is what it looks like. I know it looks a little tough, a little crazy, but that's how it works. If you have 8 in the outside shell, you got to jump to the next shell. Okay? Let's do another one. And yeah, we're going to do a pretty tough one right now. So we're going to do X, and it's going to be 34. I got 34 electrons to mess with. Now watch this, because you're going to get confused. 34. Well, you know the first 2 shells got to be filled. So, here we go. 1s2, 2s2, 2p6. So I have 2, 2, and 6. I've got 10 of those electrons. I got 24 electrons taken care of. I have 24 more to fill. So now I go to my 3rd shell. 3s2, 3p6. So let's see how many I've used. That's 14, 15, I've used 18. Now, I've got a bunch more electrons to use. But here's the problem. Look how many I have right there. I've got 8, and that's my outside shell. So rule, if I have 8 in the outside shell, I got to jump to the next shell. So my next shell is the 4th shell. Now watch, it gets really tricky. So I'm going to jump to the 4s2. Now watch. How many electrons have I used? I've used 20. I still have 14 electrons left to mess around with. But the big deal is is the third shell the valence shell anymore? No. The fourth shell's the valence shell. So what I can do is now I can go back and fill up the third shell. It's called backfilling. So now I'm going to go back and fill up the third shell. See if I can. The next one is 3D. And since I have 14 electrons left to mess around with, D only holds 10. So it's 3D10. Now, that's called backfilling. Now watch, how many electrons have I used up now? There's 10 there, 20. I've used up 30 electrons. I only have 4 electrons left to mess around with. Where do you think they go? Well, the third shell is totally filled, so they must go in the fourth shell. So 4p, and I have 4 electrons left, 4p4. So now let's do the dash. The dash, 2 in the first shell, 8 in the second. Now I have 2, 6, and 10. I've got 18 in the third shell, and I have 2 and 4. I've got 6 in the last shell. So now my valence shell is this, and the number of valence electrons is 6. Remember a rule, it's hard to do. If you have 8 in the outside shell, you got to jump to the next shell. Put some in there. If you still have some electrons left, you got to jump back and fill up the shell. Okay? That's pretty tough. We'll do a lot more of these. But for right now, we got to do this. Now watch. What if I ask for filled shells? How many filled energy levels or shells do you see here? So I'm going to go like this. Filled shells. 2 in the first shell, 8 in the second, 18 in the third. They're all filled. That's not. So filled shells would be 3 filled shells. 2, 8, and 18. Next would be number 2, filled subshells. All right, let's look at filled subshells. Remember, subshells are S, P, D, and F. If S has 2 above it, it's filled. P has 6 above it, it's filled. D has 10 above it, it's filled. F has 14 above it, it's filled. S2, that's 1 filled shell, subshell. 2, 3, 4, 5, 6, 7. P would have to have 6 in there. It doesn't. So I have S2, S2, P6, S2, P6, D10. I have 1, 2, 3, 4, 5, 6. I have 7 filled subshells. 7 filled subshells. Now the next thing is, and this is a hard one to do, how many filled orbitals? This will be number 3. Number 3. Now watch how we do this one. S only has 1 orbital, it's filled. S, 1 orbital filled. P, 3 orbitals. 1 in each before 2 in any, they're filled. S, 1 orbital. P, 3 orbitals. 1 in each before 2 in any. D has 5 orbitals. 1 in each before 2 in any. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. S has 1 orbital. P has 3 orbitals. And do not forget, 1 in each before 2 in any. 4 electrons. 1, 2, 3, and 4. So, how many filled orbitals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 filled orbitals. And 2 half-filled orbitals. All right? We'll do more, but that's it for now.